We're moving on into the transient well equation. So we're going to have drawdown as a function of time. This is chapters, both chapter 5 and chapter 7 in the textbook. We'll rely on the textbook quite a bit here. We're going to use this to talk about aquifer tests. So we need to know this for aquifer tests. So previously, we developed the Laplace equation, and we did a finite difference scheme for that. That was for equilibrium flow. And it actually came from, and maybe we did a little of this, from a mass balance of a small box of aquifer. And for equilibrium, the change of water, accumulation of water inside the box, it's not changing over time. So the accumulation per volume per time equals 0. And we came up with this equation. We took the k out of this here. We said we had 1k for simplicity, and we had k times the second derivative of space equals 0. And then since there's a 0 on the right-hand side, we can divide both sides by k, and we still have a 0 over there. So we have the second derivative in space, x, y, z, and then for wells, we used x and r. No, we just used r, rather. That equals 0. For the transient case, the rate of accumulation does not equal 0. So the right-hand side of the equation that we had up here was 0. Now it's not going to be 0 anymore. So the rate of accumulation of water in the box per volume of the box, that's relative to the box, is something times the change in head with time. And that something is the specific storage. The specific storage we'll define in a little bit here. So our equation becomes, instead of this being 0 here, we have the specific storage times the change in head with time equals this k thing times the second derivative. So if we divide out the k, we get on one side of our equation, we get the specific storage over k times the change in head with time equals the second derivative in space. We're going to develop this first for the confined case, and actually for aquifer tests, we're going to assume it's confined and then make adjustments if we find out it's unconfined. We saw in the equilibrium case that the math was a little simpler in the confined, so we'll do the same thing here. So because of that, we want to use our combined term T, the transmissivity. So we'll multiply in our equation here the top and bottom times the aquifer thickness B. So we get KB on the bottom, SS times B on the top. We recognize this as the transmissivity, T, and then we're going to take this, SS, specific storage times the B, the aquifer thickness, we're going to call that the storativity. So another page or so we'll go through talk more about the storativity. Right now, just think of it as it's a property of the aquifer that tells us the change in water inside the box as a function of the change in head, or the change in head as a function of the water in the box. So we're going to actually move this back to 2D, so we'll drop off our z term, and we rearrange, and we get that the second derivative in space equals S, the storativity, over T, the transmissivity, times the change in head with time. Or we're usually working in radial coordinates. So the way this comes out in radial coordinates, we get second derivative h over x squared plus 1 over r times partial r times partial h partial r equals s over t partial h partial t. So these are the equations that we use to solve for the head and draw down of groundwater as a function of time. Easy, right? Now we need to solve that thing. But first of all, let's take a little aside and talk more about the storativity. I'm going to go through this little PowerPoint. I copied and pasted some of this into your notes. But we're going to use pump tests to determine aquifer properties. So when we start pumping on a well, we have some drawdown. And we did the equilibrium case, but it actually takes a while to get there. To determine the storage properties, we need to know the drawdown with time. As we said with equilibrium, we start out, we have an initial head, and then we have the head after drawdown. Now it's going to change with time again. And the difference there is the drawdown between h0 minus h. Sometimes we call that a little s. As we said before, we have a lot of s's and we're adding more. And we could do this at several different radii. So we get the drawdown curve in space or whatever. We're going to have a drawdown curve with time in a little bit, so a little different curve, a little different thing. We're able to develop the equilibrium well equations just using Darcy's law. But we need more information to describe the time-dependent behavior. And that's the storage properties. So we already did this and actually pasted this into earlier notes. The specific yield, which is used for unconfined aquifers, is the volume of water released under gravity drainage from a volume of initially saturated material divided by the total volume of material. So it's the fraction of volume of water that drains out, the fraction of the whole volume. So if I have my 1 cubic meter box there, it's got sand in it, groundwater material, and then I let it open up the bottom and I let it drain by gravity. I got a screen in there to hold the sand in there, and I get 0.1 cubic meters out of there. That means my specific yield is volume drained, 0.1 cubic meter over the volume total. The total box is 1 cubic meter is 0.1. The specific retention is what's left behind. So it's the volume of water retained, and so it's volume of water retained over the volume total against a fraction. And so the released plus the retained is the total, so that is the porosity. So under initially saturated means the whole porosity, whole pore volume is filled with water. We let it out, some of it drains out, in this case 0.1, and then some of it's left behind. So if the porosity is the 0.3, for example, then the specific yield here would be 0.1, and the specific retention would be 0.2. If you have a gravel, just about everything drains out. I'm just going to leave a little wet, so it's not going to all drain out. Whereas if you have clay, it's just going to drip out a little bit of water. Most of it's going to be retained. Now, for a confined aquifer, it's a little different story. First of all, we're going to define the specific storage. That's the volume of water released per unit volume from storage under a unit decline in hydraulic head. Okay, so this here, we dropped the water level in this one. It was full to the top, and then we opened up the box, so the water level is at the bottom here. It's gone. There's some water still stuck behind. In the confined case, the box is full of water when we start, and it's full of water after we let water out. So it's still full of water. So instead of the water dropping here, just the head drops, the pressure drops. So watch this pressure meter here. So I open it up, I let out water, and let's say 0.01 cubic meters comes out. I just open this up and let it, as much come out as will. When I drop the head by 1 meter. So did you see my little gauge there? So the head drops, the pressure drops by 1 meter. It's still full of water. So in this case, with these numbers, the specific storage is the 0.01 cubic meters that came out divided by the volume of the box, 1 cubic meter divided by the head change, which was 1 meter of head. So the specific storage in this case would have units of 0.01 meters to the -1. So it does have units. The specific yield and specific retention are fractions. They do not have units. This one does have units. Now the storativity, sometimes called the storage coefficient, again, this is for confined aquifers. This is the volume of water released or taken into storage per unit of aquifer storage area per unit change in it. What does that mean? All right. So let's say I got a confined aquifer here. I got an aquifer thickness of 3 meters. Let's put a well in there and let's define a 1 square meter area here per area. Well, how much volume is underneath that one area? Well, it's 3 meters thick, aquifer thickness. That means I have 3, I'll come back to this second. That means I have 3 boxes, each 1 cubic meter. So keep that in mind, that's 3. So the storativity or storage coefficient is defined as, or is the specific storage, that's the previous slide, times the aquifer thickness. And where that comes from is, again, specific storage volume of water released per 1 meter cubed of aquifer volume per 1 meter change in head. So if I pump this out such that, again, it's full of water when I start, full of water after I pump, but the pressure drops by 1 meter, and some water comes out, and let's say it's the previous one, we said the specific storage was 0.01 meters to the minus 1, or 0.01 meter cubed released per box when that head changes by 1, drops by 1 meter. So for one area, 1 meter squared of area, I have 3 meters cubed of volume because my aquifer thickness is 3 meters. So those are my 3 boxes there. So the storativity or the storage coefficient for this aquifer would be the specific storage, 0.01, that's the previous slide, times aquifer thickness of 3 meters. So you have 0.01 meters cubed released from each box when we drop the head by 1 meter. You have 3 of those boxes, so the volume released is 3 times 0.01 divided by the area here, which is 1 meter squared, divided by that 1 meter. We have a meter cubed on top, meter cubed on bottom is 0.03. So the simpler way to look at it would be just take the numbers, 0.01 meters to the minus 1 times 3 meters, the aquifer thickness, so you get an S of 0.03. And a typical storativity is somewhere between 10 to the minus 3 and 10 to the minus 5. Somewhere in that range is a typical storativity or storage coefficient. So I pasted some of that PowerPoint into your notes here, but returning to the notes, what we do for a pump test, again, we start out assuming confined, and then we calculate the transmissivity and storativity from the drawdown versus time. What we've solved that partial differential equation above. We'll talk in next video on how we did that. And then we look at it and we say if the storage coefficient or the storativity is about 10 to the minus 3 or lower, we have a confined aquifer. If it's greater than that, we probably have an unconfined aquifer, and then we kind of need to decide what we're going to do with our pump test data, whether it's useful for us or not. So where does the water come from? Well, unconfined, it makes sense. It just drains out, right? It's caught in the pore space and drains out. So the storativity really is just the specific yield. For the confined case, water is pretty much incompressible, tiny bit compressible. If we just relied on the squeezing of the water, we have a specific storage of like 10 to the minus 6 meters to the minus 1. But we also say it's from compression of the aquifer. So it just kind of squeezes everything a little bit. Let's do a little example problem playing around with the specific storage and the storativity. So we have here a controlled research site has used sheet piling to isolate a 40 by 40 foot area of a confined aquifer, just so we conveniently have a area and volume there. We actually did that in a research study that we were part of at the University of Oklahoma at Hill Air Force Base in Utah. We actually did this, use sheet piling to isolate little cells at a groundwater contamination site and try different technologies in it. So we have an aquifer thickness of 30 feet. We did our tests. We come up with a transmissivity of 24 feet square per day, a storage coefficient or storativity of 6 times 10 to the minus 4, and a porosity of 0.25. What is the hydraulic conductivity? Well, remember T equals KB, where B is the aquifer thickness. So K equals T over B equals 24 feet squared per day over aquifer thickness of 30 feet equals 0.8 feet per day. So the units of hydraulic conductivity look like a velocity. Units of transmissivity has something squared per time, and it'd be feet per day. What is the specific storage? So we said that the storage coefficient, or the storativity, equals the specific storage times the aquifer thickness. If we want the specific storage, it would just equal the storativity, or storage coefficient, over the aquifer thickness, equals, what was our number? 6 times 10 to the minus fourth, and that's dimensionless, over our aquifer thickness again, 30 feet, and this equals 2 times 10 to the minus 5, and it does have units. It would be feet to the minus 1. All right, now we're running our stuff in there. Some water is pumped out of the aquifer. After the test, the total head in the aquifer is 50 feet less than it was before. So the head went down by 50 feet. What volume of water was pumped out? Let me go back up here and look at the definition again. So the specific storage is the volume of water per unit volume released from storage under a unit decline in hydraulic head. So specific storage is the volume of water released per unit volume. Oh, wait. So the specific storage in this case is 2 times 10 to the minus 5, 2 times 10 to the minus 5, and as units of feet to the minus 1, or I can think of that as feet cubed of water released, I'll put released, per volume, feet cubed of aquifer, per feet of head, right? So I multiply that times our volume of aquifer, which is 40 feet times 40 feet, 1,600 square feet, times an aquifer thickness of 30 feet. So it's the volume of the aquifer is 4,800 cubic feet, 48,000 cubic feet. So this cancels out. Volume of aquifer times 50 feet of head change. 50 feet of head. So that cancels out with that. And that turns out to be 2 times 10 to the minus 5, blah, blah. I have it right here. It would be 48 cubic feet is the amount that went out. So the volume out was the 48 cubic feet. Now let's reverse this a little bit. Doing another test, 300 gallons were pumped out. How much did the head drop? Well, 300 gallons times 1 cubic foot per 7.48 gallons was 40.1 cubic feet. So up here, the volume out was, we took the specific storage times the volume of aquifer times the change in head, right? So here, the change in head then would be the volume out divided by the specific storage and divided by the volume of the aquifer. And so that would be the 40.1 cubic feet divided by the specific storage, which was 2 times 10 to the minus 5, and had units of feet to the minus 1. And then also on the bottom there, we had the volume of the aquifer, which we said was 48,000 cubic feet. And I should have cubic feet 1 over the minus 1. Yeah, so that comes out the right units. It's going to be units of feet. And that turns out to be change in head equals 41 or 42 feet. So that's a little playing around with the definitions of the storage coefficient and the specific storage. The storativity and storage coefficient, I'm intentionally using those kind of interchangeably. And then the specific storage has the S sub S. The storativity is dimensionless. The specific storage has dimensions of feet or meters to the minus 1. All right, so the next one we'll move into how we're going to use this for aquifer tests to calculate the transmissivity and storativity.